we left off in the last video after discussing these very trivial solutions where you either don't do any pre-processing. That was the scan-on-demand solution. Whenever someone asks for a arrangement query, you just scan the range in the array. That's fine, except that the range can be the entire array, and so the query time is not that great. The opposite extreme was we pre-compute every possible query because there's essentially n² choices for I and j, n² over 2 because they're ordered, but let's not be too picky. You have essentially a quadratic number of choices of range minimum queries for a given array. So we might as well pre-compute the answers to all of them and store them in one big array. That was the pre-compute all solution. The query then becomes trivial. You just look up the corresponding value, but the pre-processing time goes up. Cubic naively, but you can do it at least in quadratic time if you're a little smart on it. But of course, that's not quite good enough. These two solutions are simple. How can we possibly improve upon that? It seems you have to do some storing of pre-computed values to get along, but how can you save on the space? And notice here, this running time of the pre-processing step is as good as possible as long as we store all of the solutions. We already spent just a constant time per entry of this array. So the time of pre-processing is basically dominated by the time we need to write the results, to write our data structure, which consists of this large array. So the question can also be phrased as, how can we reduce the space usage of this data structure? And that's what we'll look at next. There is one simple, nice trick that's not very complicated, but it does get a significant reduction in the space. And that's the first non-trivial idea on this topic. So let me also slow down a little bit, despite all the coffee I had. We'd like to do something like the pre-compute all solution, but we don't want to keep all entries. We need to reduce the space. So we only store the entries, the minimum index for I and j, for certain combinations of I and j. Namely, if the length of the range that we span is a power of 2. That's what this condition expresses in formulas. But really it says only if I and j have distance a power of 2, we store this entry. For any other ranges, we don't store the entry. We still have n choices for I, but then for any fixed I, we only have log n choices for j, because the total length is n. There's only roughly log n powers of 2 between the numbers 1 and n. So the number of entries is n log n instead of quadratic. That's a significant achievement. And there's even a smart way to store these entries by choosing a different index. Instead of choosing beginning index and end index, we now choose beginning index and power of the length of the range, right? That's the same k as here. But that's not the tricky part. The tricky part now is we only store a couple of these entries. How can we still solve any possible arrangement query? So how do we do this? It's fine that I'm hiding part of the solution at the moment. I want you to focus on the picture first anyways. The trick will be that we can use the information to puzzle together the answer of the overall query from a small number of queries that we do have. And in this case, this red range is the actual query we're interested in. And it stretches from 5 to 18, so that's a length of 14, if I'm not mistaken. And that's not a power of 2. 14 is not a power of 2, so we don't have this value pre-computed. What we do have is, starting at I, we have the 8 length range. That's the blue one. And we have this green range, which is also length 8, which ends with 18, with position 18. Now, in general, we can always find some power of 2 that's between the total length of the array. If we have exactly a power of 2, we don't need to do anything smart. At the other extreme, it could be so that we just touch with the green and the blue part. Actually, they always overlap by 1, otherwise you would have a next smaller power of 2. But it doesn't really matter. It would be enough if they just touch. So how can we puzzle together our arrangement query from this? Well, it's easy. The minimum in the overall red range must be somewhere in that range by definition. And in particular, it can be in the blue range, or it can be in the green range, or it can be in the overlap. But no matter where it is, it's one of 2 numbers. It's either the minimum of the blue range or the minimum of the green range. Right? That's the property of the minimum. If I have the smallest number in the blue range and the smallest in the green range, I can compare those two, and then the smaller is also the minimum of the entire red range. And so that's spelled out here a little bit more carefully with the indices worked out. We define our k like this, so that we have a power of 2 that's between the length of the range and half of that. And then we can cover this range by 2 ranges that have a power of 2 in length, a blue and a green one, as shown in the picture. You can work out what their indices are. And then the arrangement query, the red big query that we're interested in, so this is the red box, that is the smaller of these 2. So it's, well, argmin says it's either RMQ1 or RMQ2, whichever makes A of RMQ1, RMQ2 smaller. Okay, so that's just a fancy way of writing. If this is smaller, then return RMQ1. If A of RMQ2 is smaller, return RMQ2. And these 2 are just the arrangement queries from the blue and the green range. And these we have stored. So we can use our lookup table to obtain the answers to the green and blue recursive query. It looks recursive, but it's not really recursive. This is something we've stored in our table. And to be explicit, we could actually give the exact entry here if we had the space. Maybe I put that here. So we take the starting index in the first coordinate, and then the second coordinate is just the length. So that's actually easier than specifying the arrangement query. And we can do the same thing for the other one. Here it's not quite as nice because we have to copy this nasty expression for the starting index. But still not too bad. That way. So this is just 2 table lookups. And then finding which one is smaller is just looking at these 2 positions in the array and returning the smaller one. That was still fairly easy to do, right? But we got the space down from n log n, from n squared to n log n, at the expense of making the query twice as expensive if you want, but it's still a constant and a small constant. Instead of returning just 1 entry from an array, we take 2 entries from a table and compare the array entries. That's still very efficient. I haven't talked about the pre-processing so far. This was just how to solve the queries if we already have this 2D array m prime computed for us. If you think about it, the pre-processing is very similar to before. We can reuse the information that we've already computed to speed up the process, the pre-computation. If we would do it naively, so maybe this is worth writing down. If we would do it naively, we're essentially still paying a linear cost for some of the entries. So if we would just find the minimum in each step, we would have n times the size of the table. And that's still quadratic and actually a bit more. It's not as bad as the cubic that we've had before, but it's also not quite what we want. but we can do it smarter by exploiting again the recursive structure of arrangement queries. If I have a range I up to I plus 2 to the k, then I can always chop that up into 2 halves. So there's a first half and a second half. And these are actually already computed, because this one goes from I to I plus 2 to the k minus 1 minus 1. So that is just m prime of I and k minus 1. And the second range similarly is m prime of I plus 2 to the k minus 1, and then k minus 1. So I can do the same trick that I do in the query. Instead of pre-computing the minimum in the large black range from scratch, I can use that I've already computed the minima in these two smaller ranges, and then the minimum in the big one is either the minimum of that range or the minimum of that range, and I can find out which one it is in constant time. So we've used the same trick twice, both in pre-processing and in answering queries. If you have a big range, you can decompose it into two parts if they're touching or overlapping. The important part is they have to cover the entire range. And you've already computed the minima in these ranges. You can just take those minima and compare them instead of the entire range. That will be the key technique to speed up arrangement queries also in the more sophisticated solutions that we'll cover next. But it's important that you understand this part here in the sparse table solution, where it is still fairly nice and clean. The two subranges are always a power of 2, hence you've already computed it. For the pre-processing part, we just have to make sure that we compute things in the right order. So going from the small ranges to the big ones, that was the same in the last part. The pre-compute all solution also needs, for this n squared pre-processing time, you also need to compute the solutions in the right order, but that's easy to do. And with that, we get an n log n pre-processing time constant query time solution.